So, um, some of these are going to be familiar from last year. I thank you again for inviting me back. I look forward to time to actually be in Montevideo. And uh, lo siento, yo no hablo español, but I'll try to learn a little bit before the change of the year. So there are um, methods to look at oxygen in tissue, but they all have their strengths and weaknesses. So, for example, the traditional method, the Clark electrode or seahorse that Suman mentioned, they're really looking at large numbers of cells. You're looking at a bulk measurement. And as both Suman and Michelle pointed out, heterogeneity is really important, and we'd like to image these sorts of things. MRI has imaging and has great penetration into tissue, but is really limited for practical reasons to millimeters. There are optical absorbance methods done with the tips of fibers, but again, this is mainly a bulk measurement, not cellular or intracellular level. And the first attempts to do cellular imaging with of oxygen were generally done with phosphors, where phosphors were directly quenched by collision with oxygen. But most of these are, little rocks that tend to be toxic, and it's hard to target them within cells. That said, there are commercial versions, and I'm not endorsing them, but I'm telling you that we use both the oxoplate method, which embeds a phosphor underneath the cells in the plastic, or there's another method, a Mito Express, which is a phosphor that you can sprinkle onto cells and try to recover some sort of broad lifetime measurement of oxygen in microplates. What we do is of course very similar to what Suman and Michelle were talking about, is to look at either NADH or our own design probes using two-photon microscopy and FLIM. In this case, we do use the Becker and Hickel method. Sometimes we Fourier transform and sometimes we don't. The only unusual part about it in this FE1000 is that we have a special chamber to equilibrate gas with the thin layer of media that's above the plated cells. So FLIM, as you saw, can look at metabolic state. It's also a really great tool for looking at FRET. And as you know, FRET is a system where the donor is pulsed and the population goes into the donor bucket, and it normally drains at a certain rate that's the lifetime of the donor. And if you introduce near it an acceptor, this opens another channel. And so the donor fluorescence drains more quickly. And this is the usual method when people look at FLIM, is to directly record the shortening of the lifetime that occurs in the presence of the acceptor. And I'll remind you that this is something that we could do even in tissue, perhaps even a millimeter or so. And the small changes in the path length of photons coming out are not going to perturb this overall picture of a shortening lifetime. So the sort of thing that you would see is that there's a movement of the phasor towards a shorter lifetime to the right, and a certain broadening because there are multiple ways that. Let me get a pointer. I'm sorry. There are multiple ways and strengths of FRET that occur due to angle differences. So there would be a broadening of the envelope as well. I'll also mention that if you don't have a dark acceptor, but a oh, it's not letting me do that with the pointer. Sorry. I have to turn the pointer off. If you had a visible acceptor, you would be able to see that it has a delayed rise that I show with the gray arrow here. And this negative amplitude exponential would appear for the acceptor as something outside the fundamental circle, if you were able to observe both. So how did we decide to do FLIM to observe oxygen? Well, we put an oxygen responding molecule that changes color when oxygen is bound, myoglobin, in close proximity to M. cherry. And we do this. Myoglobin is the reason that if you go to the grocery store and you see a steak that's gone beyond its time, it should have stayed in the grocery store, and it gets that gray color. It's because the myoglobin has changed spectrum. And the way this appears in absorbance is that the oxygenated myoglobin has a dual peak and is somewhat blue shifted, but when it is deoxy, it's lost its oxygen, usually due to anaerobic bacteria and so on. If it were a piece of meat, this tail moves to the red and it starts to have what's called the Q band. And so there's much more overlap with M. cherry. So deoxy, there's more overlap, oxy, less overlap. And as a consequence, the lifetime is going to be shorter for deoxy. And we see that somewhere around 1.3 nanoseconds for oxymyoglobin on M. cherry and 0.93 for deoxy. So just as Suman and Michelle mentioned, you can poison or otherwise, in this case, the row 0 is a genetic crippling of OXPHOS. And in those cases, the hyperbolic binding of curve for myoglobin reaches a maximum because there's no oxygen consumption in these cells. You get oxygen completely permeating those cells and bringing them up to the full oxy lifetime in accordance with the KD of myoglobin. But in cells that are actively consuming oxygen, you get less of the oxy form of this probe as a function of outside oxygen pressure. And if you go into the mitochondria, if you target the mitochondria, you get even lower because you're right there at the oxygen sink. And we do this with normal hyperbolic binding curves, and there are typical minimum and maximum lifetimes that characterize the oxy and deoxy form. If, however, you don't have myoglobin present and you just have M. cherry, now you're looking at an acceptor-free state. It's the one bucket draining without other pathways, and you can see that it doesn't care about oxygen in that case. It doesn't care about poisons. It doesn't care whether it's everywhere in the cell or just in the mito. You get the same maximum lifetime. This is an important standard that we'll get back to later. So it's been mentioned how cancer cells alter their metabolism under various stresses, and that there is a progression towards higher oxygen consumption for more proliferative cells. We took a group of cells like that. A549 are the most metastatic, PC3 are the less, and you can see that they follow that order in terms of what we measure as their internal oxygen versus what's being applied in the media. You can see that A549 reduces the oxygen levels lower than HeLAs or the slower, less active PC3s. So this is an alternative way to look at the OXPHOS system. One can certainly look at NADH and NAD, get redox ratios. That's sort of one view of the OXPHOS system. The other is to look at how much oxygen is being consumed, which can be done in bulk, or look at the levels that it's being brought down to, which is this direct imaging. So in fact, if you look at the same sets of cells, you see that as you reduce the oxygen that's being supplied, they switch from oxphos to glycolytic. And what's interesting to us here is that that switch occurs at different levels of oxygen for the different metastatic levels in the cells. So this has, been a useful tool, and we've applied it to several systems, but we've been troubled, and so have our critics on our review panel, because there's a prevailing belief that's been around 40 years that you cannot create intracellular oxygen gradients that are significant. There were dimensional arguments made that something much less than 1/10 of a millimeter of mercury per micron was the highest gradient possible. And yet, when we looked at the heterogeneous systems, we not only saw gradients on the order of a millimeter of oxygen per micron, we also saw that the actual levels inside these cells were much less than what was being applied. So we wondered, what kind of artifacts are we dealing with? What could be making this probe not report the right thing? So we looked first at what we meant by imposed oxygen. The conventional way of measuring this is to use a fiber called an oxylight probe. It basically is a phosphor bead at the end of an optical fiber, and the lifetime of the phosphor in this bead is being measured as a function of the oxygen that's applied above the medium. So you can see that this bead probably averages over great distances. It's smaller, of course, down near the cells. So somewhere in about 100 micron region is the average distance where it's collecting the average over this bead, the oxygen. We are concerned about whether then there were Z gradients being produced. So what were our worries? Well, my first worry was hemolysis. If heme came out of our myoglobin, it would kind of look like oxy, but it would actually be producing a somewhat larger lifetime. It would be just look like M cherry alone. And we consistently see that those hyperbolae only end up around 1.35, 1.33. So in addition, we did things like put EYFP into a sandwich probe on the same material, and we would have expected that overlap changes in the other direction, and that lifetime would have increased, and we never saw that. The Z gradients I'm going to address in upcoming slides. We are concerned about the index of refraction because a higher index medium reduces lifetime by increasing radiative rate. There were also reports that fluorescent proteins were temperature dependent. So the way we tested that, of course, was that first slide I showed you about M cherry. And the M cherry lifetime in the absence of myoglobin was absolutely constant with oxygen. And it was also, although I don't show this to you today, spatially invariant. So neither index of refraction nor temperature changed M cherry itself. We also worry about aggregation, where you might have fret accidentally occurring in aggregates, but then you can change the amount of transfection time or levels to make sure that aggregation doesn't occur. Denaturation worried us because a lot of mitochondria kiss lysosomes, but we did some studies with lysosome versus mitotracker, and we found the lifetime did not vary between lysosomes and mitochondria. We also worried about maturation of the chromophore, but that should only affect intensity but not lifetime. So we think we've been pretty exhaustive in going after this. The one remaining worry was, what about Z gradients? What about gradients out in the media, not just in the cell? So we got together with Nicole Morgan, who makes the kind of pattern substrates that Michelle was talking about, and her postback, Andrew Sedlak, to do some COMSOL modeling of diffusion of oxygen in and around cells. And this is the unit cell that he developed, and he threw mitochondria in a typical pattern inside this model cell, which was about 25 micron. And he just made the unit cell to take up a quarter of it for computational space, and used symmetry repeating around the other 3 panels. And the kind of things that we started to see are that even down at 20% confluence, where there's 8 times the free space, you still get some significant multi-millimeter gradients occurring in the medium. This is a 30 micron bar here, and we wondered, just how strong that was. I should tell you that the modeling parameters that we used in this case were those of honeybee mitochondria and water as the key. So consumption rate honeybee, diffusion rate water. If you started to get more confluence by shrinking the sides of the unit cell, you started to get much more severe gradients. And in fact, we now think that a major reason that we get the gradients on the differences between external and internal are because of these large Z gradients between where we measure the oxygen out in the media and inside. The inside the cell gradients we still believe. So we do other time-resolved measurements in the lab. We look at RNA aptamers, we look at pH, we of course do NADH free bound ratios, and we have a variety of other uses with collaborators. But the one I want to talk to you about is we also do femtosecond resolution work. And we no longer do that in my lab. We now do it in collaboration with Zhanhua Xu in Shanghai. But the method which allows you to look at very early events is something that's not very familiar. It's called upconversion. You take 2 pulses from the same laser, one in the infrared and one synchronized to it in the ultraviolet. You pass that into the sample with the UV and a half-wave plate controlling the polarization, and the fluorescence is collected through filters and passed into a mixing crystal, typically BBO. With a delay, the infrared pulse also passes through and interacts with that crystal. And this is sort of like, you can imagine the fluorescence as being like turning on a garden hose. And as the water is flowing, you're taking a cup and swinging it quickly through the path of the hose and collecting an amount, and then passing it to somebody who slowly weighs how much you've achieved. So now you don't need a fast photomultiplier. Now you're simply quantifying the amount that you've chopped out of the stream of fluorescence. This gives you unprecedented timing, something similar to the pulse widths themselves. And now if you change the delay with a delay stage here with mirrors, you can trace out the entire fluorescence behavior. So what we applied that to is mainly protein work, and we studied tryptophan for a long time, and we found that there were a lot of what we call dark states. By that we mean very fast decay components that consume some of the amplitude, some of the population. And this is our most recent co-authored paper with Zhanhua, who's now in Shanghai, and they've just escaped shutdown. I hope they don't get shut down again. And we found that NADH also has dark states, but only in that folded conformation that Suman and Michelle both talked about. That's something like a third, well, a quarter, let's say, of these molecules, when they're clamped together, are completely dark on the timescales that we normally measure lifetime. But when we bound it to LDH or MDH, which are typical dehydrogenases that people think are the main contributors of the so-called bound signal, we didn't find this dark behavior. And the way we look at this is through what we call decay-associated spectra. In other words, the intensity profile is a surface, both in wavelength and time, and there are spectra that each go with a characteristic lifetime. And what we found is that the bound material shows this green fast spectrum. It has nanosecond spectra as well, but this green fast spectrum of just a couple of picoseconds is typical of water relaxation. In other words, there's a positive region here because the blue side is quickly going away, and there's a negative region here which represents that rise on the red side, and it crosses somewhere near the middle of the spectrum. However, the free state is positive almost everywhere except the very end, and the crossover point is way out in the red, which, by the way, this gives you an opportunity later. So what we observe here is something that affects the numerical value of free NADH. But I want to assure you this would not affect the sort of things Suman and Michelle were telling you about the metabolic trajectory, because one has developed biological endpoints for those two phasors, and the fractional intensities between them are still representative if you divide by lifetime. The fractional number of molecules that are present free or bound. So qualitatively and quantitatively in the biological endpoints, this doesn't hurt you. It's only when people start to do the kind of modeling where they have to know the actual concentration that's present at early times, the true concentration of free and bound NADH is the only time that this is going to be relevant. And there's also a way to get around this, which is that the correction is wavelength dependent that one could make. And by going off to that red side and centering at the crossover for free, you can eliminate it. So if you set your filter, say, to 475 plus and minus 20, you're not going to have to worry about this correction at all. What's more interesting is we can now look at that to see whether it's just the shuttle dehydrogenases or whether it's the electron transport chain proteins themselves that are contributing the so-called bound signature. And I think that by looking at these early times, especially using a stimulated emission microscope, we're going to be able to distinguish bound sites from dehydrogenases versus those of ETC and other components, especially, for example, the sort of lipid drops that were mentioned before.